Greetings, everybody. So today we have got to look at a very interesting question. Now that you've already read the question before the start of this video, let us begin with the solution to this question. In the question, you have a sphere of radius r. So that's a sphere, dear friends, of radius r. And then on the sphere, you have a tiny little bit of marble, and the question to you is, at what angle does the marble leave the surface of the bigger sphere? At what angle does the tiny marble leave the surface of the bigger sphere? That's the question to you. Let us say the angle at which it leaves the surface is theta. Theta is the angle at which it leaves the surface. Now, you can take a guess about what are the things that the tiny marble, the tiny marble leaving the surface of the bigger sphere depend on. What are the factors on which it could depend on? Could it depend on acceleration due to gravity? Could it depend on the radius of the bigger sphere? Let's try and find out. Maybe all of these guesses are going to lead you to a surprise. Let's see. Dear friends, first thing that you need to see is the forces acting on it. There is an mg force acting in the downward direction, and the only centripetal force, the moment this marble is going to leave the surface, the normal reaction due to the surface, the bigger sphere's surface, is going to become zero. So that's why the only centripetal force, dear friends, becomes mg cos theta. Because this is theta, this also is theta. So the component of mg in this direction is mg cos theta. That's the only centripetal force available. So if you wrote an equation, dear friends, it would look like this. The centripetal force, which is mv square divided by r, is solely provided by mg cos theta when the tiny marble leaves the surface of the big sphere. Well, of course, you should know that small m is the mass of that tiny sphere. Well, you have m and m getting cancelled. You can just write v square equal to g into r into cos theta. I'd like to call that equation 1. Let me call that equation 1. Now that we understood that these are the forces acting on, this is basically a force analysis. Now let's also do an energy analysis. Well, to begin with, the mass, if you took this as the origin, the mass was at a height r, dear friends. Now, if you see what's the height, it has certainly reduced. Before it was r. As you can see, this, my friends, is the adjacent side for the right angle triangle of the right angle triangle. That's here. So this length certainly should be r cos theta, because it's the adjacent side. Once you know that, you will be able to calculate what's the difference in potential energy. The potential energy in this place is mgr, because it's measured from here. It's at height r, m mass into acceleration due to gravity into the radius. What is the potential energy once it is just about to leave the surface? It is mgr cos theta, because the height now from the chosen origin is r cos theta. That's theta. Now the difference between the potential energy has transformed into kinetic energy, half mv squared, right? Now, if you just cancel out m from this equation, then you will have v squared is equal to 2 into g into r into 1 minus cos theta. Into 1 minus cos theta. Well, you have equation 1 and you have equation 2. On both the equations, LHS is the same. You can equate the RHS, dear friends. We are now up for a surprise. gr cos theta equal to 2gr into 1 minus cos theta. Now you see, gr and gr gets cancelled. That's so beautiful, because it turns out that it neither depends on acceleration due to gravity, nor does it depend on the radius. Dear friends, cos theta now becomes equal to 2 minus 2 cos theta. 2 minus 2 cos theta. Bring this cos theta here, it's going to be 3 cos theta equal to 2, or theta would become equal to, maybe I'll write it here, theta would become equal to cos inverse of 2 divided by 3. That's a fascinating result. It's a mind-boggling result, because Probably when we started off with this question, there were a lot of questions that were in our head about what are the things that the mass leaving the surface of the bigger sphere depend on. We thought it's going to be acceleration due to gravity, length, it could be the radius. It turns out it doesn't depend on anything at all. So whether you do this experiment on the planet Earth, on the moon, or any other planet in the solar system, my friends, this tiny marble here is bound to leave the surface of the bigger sphere exactly at the angle cos inverse of 2 by 3. That's a fascinating result. It was great talking to you in this video. The feedback and comments are welcome. Thank you so much. Have a nice day.